Hello, this is Team D2-Vision. I will begin a presentation from now on. The presentation will be progressed as follows. First section is project outline. Our goal is to make it possible for driving assist only with the vision, not the other sensor. Therefore, we progressed lane detection and object detection research as below.
The second section is object detection. In previous project, we used V4 as a main object detection model, but it is too heavy to run in both the car and road, and the dataset was so limited in the environment. So we need a faster, lighter, and more accurate detection model and more diverse and plenty of data in various environments, plus with great accuracy. In order to satisfy the following requirements, this semester we focus on these three elements. We changed the detection model to Sentinel-2, known as a faster and efficient model. Changed the dataset to Cocoa dataset, a highly scalable dataset format. And repeated experiments to determine hyperparameters which can achieve higher accuracy. The existing ULV4 is a one-stage detector method. It has a heavy classification and box regression head, but Sentinel-2 uses a probabilistic two-stage detector method. It can provide increased accuracy and speed with probabilistic two-stage detection. This is how Sentinel-2 works. Step 1. Find the probability of the object. Step 2. Conditional probability classification. According to the paper, Sentinel-2 has a better AP than ULV4 when using the same Cocoa test dataset, and its real-time object detection also shows faster runtime and higher MAP. We changed dataset format from existing YOLO to Cocoa. Cocoa format has high scalability and provides some object annotation data in their official website. You can see that YOLO format only stores bounding box information, but Cocoa data format has various information, not only bounding box, but also segmentation information. To construct datasets, we annotated custom data using the LabelMe program. Moreover, we extracted person class images and annotation data from Cocoa dataset 2017 for getting a large amount of dataset acquired in more diverse environments. After that, we annotated with LabelMe with converted to the Cocoa dataset. And this is an image with segmentation information. This table shows composition of our train and test dataset. We got person data from Cocoa dataset, and we collected con data ourselves. And then we repeated experiments and optimized the hyperparameter value. The AP information came out as follows: vintage size 8, learning rate 0.0025, iteration 6000. We published class, object probability, x, y minimum, and maximum coordinates of detected object using custom RS message. The coordinate change depending on the size of the image, so we need to discuss it with the control team. When threshold was set to 0.3, the cone recognition performance resulted in like this. As you can see, ULV4 is not very good at detecting distance cones. However, Sentinel-2 can detect cones at a distance about 30 meters. ULV4 uses GPU memory around 2000 MB, but Sentinel-2 consumes only 1255 MB. So we can verify Sentinel-2 is more efficient in GPU usage and light computation. For MAP value, we can see that Sentinel-2 is higher than ULV4 in both person and cone class. Especially in demo test, ULV4 detected a person and cone about 5 to 7 meters. In contrast, Sentinel-2 detected a cone about more than 10 meters, and in case of person class, it can recognize even farther away. In conclusion, there seems to be need for improvement on 2 points. First, the process of classifying dynamic obstacles and static obstacles was simply divided into cone and person classes. It would be better if the tracking algorithm was applied, such as deep sort, etc. Second, we added new cone images to dataset but still limited in nearby object. Lack of distant cone data can occur overfitting in closed cone instances. Also, we have difficulty in detecting objects when they overlaps, so we need to configure dataset more efficiently.
The next topic is lane detection. Here is lane detection system of previous project, but it has something problem. The previous lane detection model was unable to obtain the coordinates of the points in the lane, and hence the curvature was not available. Therefore, three processes, ransack, sliding window, deep learning, were set in the directionally. First is ransack. Ransack is to take a sample n times and find the line suitable for the most overall appearance. However, since it takes a lot of time to process the calculation while taking samples, it is not suitable for our work, so we do not use it. Second is sliding window-based lane detection. Sliding window-based lane detection pipeline is following. Let me tell you one by one. When the input comes in, we apply camera calibration to correct distortion. The result is as below. Next, sharp filtering is proceeding with transformed images and extracting gradient. Compared to sovereign filter, we found that sharp filtering performs better. At the same time, we set the transformed image to lower upper thresholding, and we mask the yellow and white colors. To further facilitate lane detection, the thickened image is applied. And then we merge two filtered images with bitwise end. Lastly, the remaining third and pepper noise removed by 5x5 median filtering. Next, the lane is detected in the filtered image using sliding window search. Then the points are sequentially appended to the left and right lane list. The curvature is calculated after the list contains points, and it is converted to the local map coordinate system. After conversion, a message is sent to the master node. Curvature calculation and coordinate transformation proceed as follows. This is a demo video. The video was taken by manual driving because the driving is still unstable. Publish the list and curvature of lane points every moment. The limitation of this model is that it is difficult to find the optimal ROI and thresholding value. We believe that the next deep learning model will solve this problem.
There are two main methods of lane detection using deep learning method, LaneNet and PineNet. LaneNet uses the instance segmentation method and operates lane fitting. Using instance segmentation, it is able to distinguish each lane as a different color. On the other hand, PineNet uses stacked hourglass networks and estimates the exact points of lane. High false positive rates can lead to severe risks in control, so it is important to reduce the false positive rates in an effective way. PineNet was the model which has the lowest false positive rates, so we decided to choose PineNet model. Additionally, PineNet has strong performance in complex conditions such as light conditions and occlusions. PineNet's main contribution is as follows. Using key points estimation approach, PineNet could lightweight model than other semantic-based methods through producing compact size prediction output. Next, it eliminates outlier through proposed post-processing. It also can be applied to various scenes like vertical or horizontal and arbitrary numbers of traffic lines. And lastly, we can achieve safe autonomous driving through low false positive rates on lane detection. We tried to test with pre-trained model in SoundTrack using Logitech webcam C930E. As a result, we found that the accuracy was so bad, which we decided to collect our own dataset and train the model and apply a new weight value. Public lane dataset. TuSimple is composed of original picture files and corresponding JSON file which contains the annotated lane coordinates. In JSON file, raw file is specified to the picture file path, and lanes is specified to the x coordinate corresponding to the y value. H samples is specified to the y coordinate in intervals of 10. PineNet is customized to TuSimple dataset, so we need to make our dataset as a format of TuSimple dataset. We acquired 360 pictures in size of 1280 by 720 in SoundTrack using Logitech C930E webcam. To label in the form of TuSimple dataset, first we draw the y-axis baseline in intervals of 10 using OpenCV. We uses the LabelMe for labeling tool and labeled in a dotted form along the lane based on the displayed y-axis. After the labeling task, we saved the labeled form in JSON format and converted to a format of TuSimple dataset using some Python code. We judged that dataset quantity is not enough, so we used the data augmentation. Using the method of randomly controlling the brightness, raining, and cloud effects, we could get 4 times of the original dataset. We finally put together the TuSimple data and our own dataset and began the training. After the training, we could check that the accuracy was estimated as 0.96. We compared the accuracy of pre-trained model, which was trained only with the TuSimple dataset, and custom training model, which was trained additionally with our own dataset. These 2 videos are recorded with the webcam in real time at SoundTrack. As you check in this video, the performance became better after training our own dataset. A list of lanes coordinates should be published with ROS topic, then hand over the recognized lane information to the control team. We try to send a list of recognized left and right lane points to the master node. However, during this process, we could not confirm whether the accurate information was handed over. Furthermore, research on ROS topics seems to be needed to hand over the accurate information of perceived lanes. And for eliminating outlier, we need to select the ROI reason for eagle lane. Then the outlier for the other reason, except the eagle lane, will be excluded. Also, we need to test in the other environment, not only the SoundTrack, so that we could check the lane detection is working well in the severe test environments.
Last section is summary. With this semester research, we focused on basic technical research. Object detection found lighter models with higher performance. Lane detection has become able to follow the curve. I've mentioned the unfortunate part before. So, our future plan is to supplement the basic technologies and implement integrated technologies. that were not implemented this semester. This is rule allocation. Lastly, it is a reference. Thank you for your attention.